Welcome to this explainer. Okay, today we have a really critical hands-on mission. Imagine you've just built this fantastic little robot. The motors are humming perfectly, the wheels are spinning, and it is cruising rapidly across the floor. But there's a massive problem. It's heading straight for a solid brick wall. If we do absolutely nothing, it's going to blindly crash, literally scattering all our hard work into a dozen plastic pieces. So how do we stop it? Today, we're exploring the core mission of sensing and programming logic. We're going to transform our robot from a mindless driving machine into a smart device capable of detecting obstacles and stopping itself way before disaster strikes. Okay, let's dive into this essential question. How does a robot know when to stop? I mean, it seems like a simple question, right? For us humans, we just use our eyes. We see a wall, and our brain instantly sends a signal to our legs to stop walking. But, a robot doesn't have a human brain. And out of the box, it certainly doesn't know what a wall is. A robot only knows exactly what we tell it. So to answer this question, we have to think critically about how a machine actually responds to its environment. We need to bridge that gap between the physical world out there and the digital instructions running inside the robot's computer brain. To get there, here's our roadmap for today. First, how robots sense. Second, the if-then decision. Third, practice, obstacle detection, and finally, testing and debugging. Section 1. How robots sense. Understanding inputs. Before we can tell the robot to stop at a wall, we kind of need to give it a way to realize the wall is actually there in the first place. So, here is our foundational definition. A sensor is a physical tool a robot uses to read input data and detect conditions in its environment. I really want you to focus on those words, input data. A sensor is literally the hardware that allows a robot to read the physical world. Think of it like a digital pair of eyes or fingertips. Without a sensor, a moving robot is completely blind. It'll just spin its motors forever until the batteries die or it hits something. By adding a sensor, maybe a touch sensor that gets pressed in, or an ultrasonic sensor that bounces sound waves off a wall, we are finally giving our robot a stream of input data about the physical space around it. So the absolutely crucial takeaway here is this: sensor data equals environmental response. This directly ties into our grade 7 curriculum's essential question: how can a robot use sensor data to respond to its environment? Simply put, gathering this input data is the only way a robot can change its behavior based on what's happening outside of itself. If we want a response, like, say, stopping, we absolutely must have sensor data first. Section 2. The if-then decision, logic and choices. But hey, gathering data is only half the battle. Now the robot has data coming in, but it still needs to actually make a decision. And this brilliantly illustrates the core of computer decision-making. We've got two contrasting statements. On one hand, we have if obstacle detected, then stop. On the other, if no obstacle, then move forward. This is called an if-then statement, and it's exactly how we program a robot to make a choice. The robot looks at the condition: is the obstacle detected, true or false? If it's true, it triggers that then action, which is to cut power to the motors and stop. But if it's false, it just continues with its default behavior of moving forward. We're basically handing the robot a very strict rulebook for every possible scenario it might face. Now, I know it's easy to get intimidated by programming, but just remember this core principle. Logic is simply cause and effect. For a grade 7 robotics student, this is a massive light bulb moment. An if-then statement isn't magic. The robot isn't thinking or making independent choices on its own. It is just blindly following a strict cause and effect rule built from your precise instructions. The cause is the sensor reading, the effect is the motor behavior. You are the architect of that cause and effect. Section 3. Obstacle detection, worked practice. All right, now that we understand sensors and logic, let's shift into our practical worked practice mission. It's time to build our actual obstacle detection routine. Here is the exact step-by-step programming flow we need to create. Step 1, read sensor. The robot constantly pulls the sensor, asking, hey, is there anything there? Step 2, check condition. The robot runs that data through our if-then logic. Is the distance less than 5 centimeters? Step 3, change behavior. If that condition is met, the robot translates that raw data into a physical halt, sending a command to brake the motors. And this loop happens continuously, literally hundreds of times a second. Read, check, change. Read, check, change. When you execute those specific steps precisely, you achieve reliable sensor-based behavior. This answers another one of our essential questions. How can precise instructions make a robot move reliably? Well, by combining basic movement commands with constant sensor reading and clear if-then logic, we fully prevent the crash. The robot moves reliably because the instructions actually account for the real physical world. It isn't just hoping the path is clear, it's actively proving the path is clear before taking every single step. Section 4. Testing and debugging. Fixing errors. Of course, anyone who has ever built a robot knows that the theory and the reality, they don't always perfectly align. So, what do we do when we test our brand new routine and the robot slams into the wall anyway? Well, now what's really interesting about this slide is how it reframes a failure. By directly comparing our expected result with our observed results, we gather vital clues. We expected the robot to stop at the wall. We observed the robot hitting the wall. We expected the condition to be met. We observed the condition being ignored. You see, in robotics, a crash isn't just a mistake to get frustrated over, it is a scientific process. The robot didn't disobey us, it did exactly what our code told it to do, which just means our code has a bug. To fix that bug safely, we follow this strict, iterative debugging process required by our unit outcomes. First, test motor behavior. Are the wheels actually plugged into the right ports? Second, check sensor input data. Is the sensor actually detecting the wall, or is it maybe mounted backward or way too high? Third, revise instructions based on those results. Actually, maybe our if-then statement said stop if distance is greater than 5 instead of less than 5. We tweak the code, we run it again, and we iterate. This cycle of testing and revising is absolutely the beating heart of robotics. Which brings us to the end of our foundational obstacle detection mission and leaves us with this really exciting thought. We've just learned how to use a single sensor and a simple if-then statement to stop a crash. But look at this question. If one sensor can stop a crash, how could you combine multiple sensors to navigate a complex maze? Just imagine a touch sensor on the front and maybe a distance sensor on the side. The possibilities for complex, intelligent behavior are literally endless once you master these basic tools of logic and environmental response. Think about how you'd code that, and I'll see you in the next explainer.